So again, thanks very much for the opportunity to be here. As Dan said, a lot of what we've been thinking about in response to what we heard, was going on, particularly during the heat wave in June, kind of comes down to a variety of topics involving groundwater supply management. And so what we thought we'd do today is start off a little bit with talking about groundwater models, partly because that's what I do, and some of their readiness for modern day needs. I'm getting involved in a lot of projects up and down the West Coast where the common theme seems to be, how do we make sure our water systems are resilient, given some of the changes we're seeing, whether it's natural and in the watersheds and climate related, to what extent it's demand driven, even regulatory driven, that kind of thing. And so we'll talk a little bit about groundwater models and how they can help with thinking about well field and water supply operations, as well as a little bit about just what it means for long-term planning. Well field operations are both a long-term and an immediate need to be thinking about at times. But there's also kind of long-term management of the aquifer and your systems as well. And there's times when models can help with understanding those things. A part that Kenny will talk quite a bit about, one of his specialty areas, is in well performance maintenance and rehabilitation, because obviously, if the system is starting to get used as hard as we heard the system was recently, that's going to be one of the first places you're looking at what you have and how it's performing is in that area. So he'll talk about that. And then Dan will finish by talking a little bit about coordinated water conservation planning, including some of the things, skill sets that we have inside GSI, where we've helped a few other clients in this area. Let me talk just a little bit about groundwater models without turning into a groundwater model geek. I'll try really hard not to do that. Why do we use groundwater models, which are models of aquifer systems and of how wells and other features in the aquifer work? When I think about, I've been doing this for 30 years, in fact, longer than that. When I think about why if people ask me to do this, and why do they keep paying me, which is a great thing, it kind of comes down to, number one, well field operations and well field management. There are utilities out there really thinking hard about how do they optimize the operations of all their assets. And oftentimes you're talking multiple wells. I'll give you an example from Portland a little later. Siting and designing new wells. We've been doing a lot of that kind of work lately, which I've been a little amazed at how much we've been doing. Can give you some insights as to how models with that. And along the way, the models often help us understand how the aquifer behaves and what effects the aquifer is having on how wells and well fields are going to perform. So we build models a lot around with that water supply management optimization concept in mind. There are other factors too. If you think about the operational effects of changing water demands, the amounts of water use, like you were just describing, Terry, the timing at which maybe you have to run a system, at or near your, peak season rates. Some of those can change over time for various reasons, whether it's maybe climate change driven, demand driven. We use models to sometimes look at effects of climate change on an aquifer system. And if there's an interconnected river system, I'm surprised how many of the models I'm doing nowadays are examining groundwater surface water interactions, whether it's water rights related, or in California, I'm doing a bunch of work that's related to protecting habitat. And the models are playing an important role down there. And then lastly, particularly on the Washington side, a lot of attention's been paid to pumping effects on the river, and that's revolved around water rights and in-stream flow questions. So let me talk first a little bit about the well field operations and how models can help. And I'm going to start by showing you some examples of the models that have been built out here in this area. The very first model that I know of was a model that looked like this built by the USGS in the early 1980s. And this was back at a time when the USGS didn't even have a standard groundwater modeling code yet. They were actually working to develop one, which they released a few years later called ModFlow, you might have heard of. But you know, they built a model that tried to represent the aquifer system, mostly on the Washington side, extending a little into Idaho, very coarse grid. Mostly it was a model they were using at the time to think about some of the issues around water quality in Spokane County and the issues with chloride and nitrates in groundwater because of the prevalence of septic systems out there. And there wasn't a whole lot of detail about the groundwater flow system. That's actually a map we're looking at. So you can tell it was pretty darn coarse in terms of, you know, what it could look at. The next model that came along was one that I really got my time up here in the region going. It was back in the mid 1990s, culminating in 1998 with a report that was for wellhead protection, initially for the city of Spokane, later also for the Spokane Aquifer Joint Board. And I'm sorry, probably not showing up real well, but if you look around the city's wells that you see there, these little clusters of dots. And this was a model that actually came out of Europe that we found really good for being able to simulate a regional flow field, but zoom in on a local area of interest, such as around a well or along a river. And we were able to do a lot with that model and actually still have in recent years. About 10 years later, the USGS came along and built the bi-state model, which some of you may be familiar with, you know, that covered the entire Spokane Valley, Rathdrum, Prairie aquifer system from Lake Pend Oreille all the way down to Long Lake. As you can tell in this model, it was using square grids. And again, they're fairly coarse. One way you can know it's coarse is because I'm trying to show a grid and it's not just all a big black blob. You can see white space in between. You know, kind of helpful for understanding the regional system for sure, especially because it's covering, you know, it covers an area that is the whole entire aquifer footprint. So its boundaries conform to the natural boundaries of the aquifer system. The city and CitySajb model actually later got expanded into that same area covered by the USGS model. It had started out as a model that stopped at the state line for various reasons related to wellhead protection being done in Washington, and they didn't want the capture zones extending into Idaho. kind of the reality of it. But later on, as time went on, it was seen that there was a lot of benefit to having a model that, again, covered the entire aquifer system. And some of the benefit can really be seen in this next slide that shows what that benefit is. The USGS model, I've overlain the black square cells, and the little black circles are just the centers of the cells on top of the grid that CitySajb model uses, which is in that light blue. And what you can see right away is that, you know, we were able to build in these, you know, fine meshes around individual wells owned by individual water purveyors and look at the flow fields at a fairly close scale and understand the hydraulics in a way that you just can't do with those larger grid block cells. And if you even if you were to just zoom in on one of those large grid block cells, here's one of CID, one of your wells, the 2A, 2B, 2C well field. I mean, look at what we were able to do there in terms of, you know, refined gridding inside what's a really large quarter-mile by quarter-mile cell in the USGS model. So lots of things that are really great to do, and you could build flexible grids and be able to really do just about any kind of analysis. And so one of the things I've been thinking about lately is that, you know, both tools have served their purposes well over the years, the CitySajb model and the bi-state model, but they're getting kind of long in the tooth, kind of showing their age a little bit. The bi-state model, of course, has a pretty coarse grid. The other thing about it is in most of the area that it's simulating that whole entire thickness of the aquifer with just one model layer. So you cannot model the vertical flow component in a one-layer model, you're essentially modeling two-dimensional horizontal flow and not capturing the vertical. So we had all along in the CitySajb model had a minimum 3 layers in that model. Because we wanted to capture that, most of the wells, particularly in Washington, were only in at the upper 70 to 100 feet of the aquifer, and there was still maybe 3, 4, 5, 600 feet of aquifer beneath that. And when you're starting to think about the dynamics of how a river and an aquifer interact with each other, plus a well, you got to have that 3-dimensional aspect to it. The thing about the CitySajb model is the software hasn't really kept up over time. So I don't know if anybody owns an iPhone 1 or an iPhone 2, but we're kind of getting a little bit in that space. Plus what happened recently and very abruptly, the developer of the model retired and I guess gave the rights to the software to some European firm I've never heard of, and I don't know how many people have. So we can still use it, but I'd say its future is kind of questionable. The good news is some terrific tools I'm about to show you have become available in recent years that are actually through the USGS, but something they've done that they really never used to do was they've partnered with some specialists in the private sector to build some really terrific flexible tools that allow you to embed grids inside a model where you want them, turn them off and on, and really not lose the local detail in your aquifer system or the regional detail while you're simulating the local detail. I'm trying to pull up a graphic. There we go. So here, let me give you some visual examples of that. One of the places I first started using this was down in Prineville, Oregon, where we had built a model maybe 7 years ago, fairly regular grid cells. The green shows where there's some river systems. And we, a couple of years later, started doing some work in one part of this that we wanted to study a little more closely. It was an area called the Airport Well Field. So we wanted to build a refined grid in there. And, the thing with the old tools was if you wanted to build a refined grid and focus on an area like right here, you had to carry all these cells out in other directions and just increase your computational burden and costs and everything really badly. Well, look down here, there's a little spot right here where there's a dense blob. And in these new tools, what we can do is start embedding grids wherever we want them and look at questions like a groundwater supply that they actually wanted to develop in that part of the basin to pipe water over to that airport well field to inject for all kinds of different reasons, kind of a complicated project. And so we built that nice little grid. This is a zoomed in view, looking at how we could, really kind of custom design a grid to look at conditions along a river, think about well locations, think about how to optimize the operations of those wells, run simulations that tell us when the model or when the wells are running, what do the groundwater elevations look like? Trying to get that to come up on the screen. There's quite a delay here. And there we go. You'll see a contour map that the high groundwater elevations are in red, the greens and blues are the low. So you can start really simulating in detail right around your area of interest. What does that drawdown cone look like? How deep is it? What's that water level threshold going to mean relative to where I've set a pump or I, have a well screen? And, really zoom in on these things and build in all the detail that you want. It's really a terrific capability. And we used to spend weeks doing these kinds of things in the old tools, and you can pretty much go outline an area with your mouse, turn it on, and, depending on the model, some are easier than others, but you can get some analyses done real quickly. The other thing, this is an example from a model I've worked with for a long time in Southern California. You can nest these grids inside other nested grids that you build. So in this basin, we had a parent grid covering the whole groundwater basin. We had a sub-regional mesh I call level 2 that was focused along river corridors and alluvial valleys. And we've done all kinds of modeling with that model. Just a few weeks ago, I actually got asked to look at a local project involving an area where they're thinking of installing 2 more wells and trying to pump harder in that area. So we just went and built another local grid right in that spot, turned it on, ran the simulations of the water scenarios they were interested in, and it's helping them with some well designs that they're working on. This one's an example from Redmond, and the city of Redmond has 5 wells in their downtown area. And I wanted to show this one to you because this is a case where we turned on multiple of these grids, all at once around each well field, simulating various things in various ways. And it's been very helpful for them to think about how to manage their groundwater supply, because they have wells that are in their urban core downtown, which the entire downtown, if you've been there, is undergoing just an incredible transformation of land uses. And they've had a lot of concerns about what does that mean for that groundwater system. Let's come back to Spokane. We've done a lot of work for the city in recent years as they started the process to build their first new water supply well in 7 decades, the Havana Street site. And this is a map from that existing model showing again where the city has all their wells, and a couple other sites they were thinking about developing, Audubon Park and Faith Bible Church Corbin Park area. But they've done work at Havana Street is where they focus their efforts. And if you look at that, tiny little blob of grid there and blow it up at Havana Street, this is what it looks like. We have done quite a bit of work helping them figure out how much could they pump and how many wells would they need from this parcel of land that they had access to. That wasn't huge. But this aquifer is so crazy permeable, you can actually pump a lot from even a modest parcel of land, as I'm sure you all know. So we did quite a bit of work with first doing a test well installation and pumping that, monitoring water levels in the new monitoring well, and at a observation well that the county's had out there for, now about 20 years. And then we worked inside this area that was identified as the footprint where we could put wells to, really study in detail, how should we lay them out, how should we pump them, et cetera. And of course, it's just a model, so we got to have good field data. We did a 5-day long pumping test of that test well, monitored the observation wells we had, monitored the river and what it was doing, which is that top line. Over here, monitored what was happening before the test started, monitored water levels on this site during the test, and then the recovery and the trends afterwards. We also looked at data at that county observation well for the prior 15, 16 years to think about how during the summer season, which you see circled in the green, some of these lowest year dry summer conditions, to us, that kind of defined the water column that we had to work with in terms of during the summer months when they want to operate that well and that well field, what do we really have to work with? And the number is really astounding that there's shallow bedrock there. And because of the way the well design would work, the shallow bedrock and these low water levels, we have about an 8-foot water column to work with to provide pumping during, for municipal supply. I've never run across that anywhere else. That makes a hydrogeologist's head explode in most places to think about trying to develop a water supply in that environment. That's just how crazy permeable this aquifer is. But we took all those data sets and then we're able to run screening level simulations, well, more than screening level, through the model to say, okay, take those data sets, take that fine model with its local detail, but also its aquifer-wide influences, and start thinking about how could you best lay out that well field in terms of number of wells, target production rate, how much drawdown you're going to get, and whether you're going to have problems meeting the production targets with just that 8 foot of water column, and trying to think about how, it is the subsurface. There is always a little uncertainty down there, and we have to take that into account in our modeling analyses. And so out of all that came the decision to build 6 wells on the site. We figured out a network to arrange them in on the site, and the city was then able to proceed with thinking about how to get those wells in the ground, and then start bidding the engineering services for it. And so the model played a critical role in doing all that work. And I just want to put this up again as a reminder, partly to myself, but all of us, that, a really good locally detailed model can go a long ways in helping us understand how to build a well field and how to run it. Now that all those examples I just showed you were mostly about new wells and well field designs. But I'm going to turn to one that we did back about 3 years ago for the Portland Water Bureau, that was all about optimizing the operation of the assets that they already have. This map, the white area, is showing what's called the Portland Geologic Basin, which has this large aquifer system in it that's basically have a large shallow regional system, and then systems at various different depths further down in the basin. The Water Bureau has its emergency well field along the Columbia River from about I-205 and the Portland Airport, a few miles east of there. And back in 1996, the USGS built really a pretty good model of that entire basin. It was coarse, but it captured everything that needed to be captured there. Starting in about 1999, continuing through 2001, I got asked to work with the lead hydrogeologist at the Water Bureau to take that model and turn it into a well field model with that local resolution. And then in 2014, do further expansion and refinements of it. And in 2018, we really put that thing to some serious use, because they were working on a master plan for their water supply portfolio. And, most of you may know that they're partly dependent on groundwater, but Bull Run, the surface watershed, is their primary supply, federally protected watershed. And what they asked us to do was to look at various demand scenarios in terms of how they would operate the wells over a multi-year basis under those demand scenarios. So this first one, and what you're looking at, are 2 plots. They're for 2 different wells. They both happen to be in the deepest of the aquifer systems. The Bureau actually has water wells in all 3 of their systems, and we looked at them all together. And what we were basically doing was saying, okay, here in the dashed red line is the cutoff level for where that well has to come off if the water level ever drops that deep. And so we had this one well where it was pretty deep, and sorry, something went haywire. And one that's a little shallower. They run their wells usually on a seasonal basis. So during the winter months, they're mostly relying on Bull Run for the water supply. They turn the well fields on in the spring, run them for about 4 or 5 months each year, maybe 6. And that's what you see in terms of the cycling of what are water levels in those wells. The blue water levels were basically accounting for their pumping plus regional pumping around that whole geologic basin. They asked us to run a model without the other folks pumping, which is the orange line, just so they kind of knew how much their contribution was. But at the end of this base demand scenario, they had us run a simulation where they said, oh, and at the end of the summer peaking season, let's assume that we had a major flood event occur in Bull Run, created turbidity problems, and we couldn't use the surface water supply. We have to go on well fields for 100% of the supply for 30 days. What would that look like? And that's what these curves were here. And we could see that this one well, it's saying, yeah, the rate you want to pump that one, you may have to back off because you're going to run dangerously close to hitting that cutoff level. This other well here, though, it's got room. Maybe if you're running the model at what you think the capacity of that well is, see if there's something that you can do to maybe increase that capacity a little bit, because you can make that up. They had us run another scenario that they call the wildfire fire scenario. What if wildfire happens in a large part of that watershed and the turbidity levels are so high that they can't use it? In this case, for 3 years was what they asked us to assume. And those two same wells, you could see they were going to run into problems each summer in this one well, but also the other well, it was going to start getting a little bit nip and tuck. So we did this for all of the 25 or 30 or so wells that they had. And they've said it's been very informative to helping them think about things in the long run. So with that's all kind of a focus on how models help with well field planning. But obviously the on the ground stuff's really important. How are wells operating now? What can we do, to look at that question? And I'm going to turn this over to Kenny Jansen. But obviously the on the ground stuff